take a look at two more examples of u substitution. So we're taking a look at the integral of x to the fourth sine of 7 x to the fifth dx. Again, when we're looking for our choice of u, that only comes after saying, can I integrate this using just regular antiderivatives? Look at this. Hopefully you can't, right? There's no way you can. So you need to instead pick an appropriate u. So I'm going to say, let u, again, choices inside parentheses are a popular choice. Now, before when we had the sine and cosine, because there was different sines and cosines, we chose sine of whatever to be the whole u. Here, I only want to choose the inside. So I'm going to let u be equal to 7x to the fifth. The reason that I'm thinking about this is because I'm eyeballing that x to the fourth. That might disappear when I take the derivative. So when I have du is equal to 35x to the fourth dx, I see, indeed, I have my x to the fourth dx that can be substituted in over here. And then I have my 7x to the fifth. So everything can be substituted in terms of u. So this was a good choice of a u substitution. So this now becomes the integral. Now again, I divide over this 35. So I have this constant of 1 over 35. The integral, the x to the fourth dx, that just appears as du. And then here, sine of this is just sine of u. So now we look for the antiderivative of sine, which we said that was going to be negative cosine. So I have 1 over 35 negative cosine of u plus a constant. So substituting things in for x and distributing terms, I have negative cosine of 7x to the fifth divided by 35 plus c. And that is my final answer. So this next one, again, we saw one similar to this. I like to approach it in a similar way. I'm going to say let u equal 2x minus 1. Du is going to be 2 dx. Now, if you've become somewhat comfortable with u substitution, you should be a little bit concerned because you have something for 2x minus 1 here. So this could be substituted in there, and you have something for dx that can be substituted there. But this x, that x is missing, right? This x right there does not have something to be substituted in for it. So you might be thinking, well, this did not work the way that I wanted it to. But there's a little added step to this style of u substitution. I somewhat like to call the sassy u substitution because there's just like a little bit of sass that we have to throw into figuring out how do I get this x in terms of u. So this equation here, saying u is equal to 2x minus 1, what does that say about x? Well, I could add 1, so I'd have u plus 1 is equal to 2x. I divide this by 2, I have u over 2 plus 1/2 is equal to x. So I do actually have something now to substitute in for that x. So this is a really useful technique sometimes to figure out how do I circumnavigate this issue where there's a term there that I don't want to be there, but I don't know how else to deal with that. So if we now work with this, I can now substitute in. So I divide over the 2. So I have my du over 2 is my dx. So I can, again, pull out the 1/2 with the du. I have this x is u over 2 plus 1/2. And I'm multiplying this by the square root of u because I substituted in the u underneath that. So that will just be u to the 1/2. Because that's the same as square root of u. Now when I see this, the immediate thought should be, I'm just going to simply distribute. Right? There's no other weird exponents, just distribute this to both of these terms. So this becomes 1/2 integral of u to the 3/2 divided by 2 plus u to the 1/2 divided by 2 du. Now, as you become more comfortable with this, you realize, wait, they're both divided by 2. Can I just pull out another 1/2? Absolutely. You can keep pulling out constants as long as you're basically factoring it out of everything. So I can factor this out. So I have 1/4 integral of u to the 3/2 plus u to the 1/2 du. Now I just simply take the antiderivatives of each of these. So when I add 1 to the power of 3/2, I get 5/2. When I divide by 5/2, I'm really multiplying by 2/5. So I have 1/4, and then I have a 2/5 u to the 5/2. And the same thing over here, when I add 1 to the power, I get 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So this is 2/3 u to the 3/2 plus c. Now I distribute my 1/4 to everybody. The constant just stays still plus c. But now I get a 2 over 20 u to the 5/2 plus 2 over 12 u to the 3/2 plus c. And that's my answer. Obviously, you can simplify the fractions, but that's not that important. Actually, it is not quite my answer yet. I do want to substitute back in for x, so this is just the middle step here. So I indeed want to substitute back in 2x minus 1. So this would be 1 over 10, 2x minus 1 raised to the 5/2 plus 1/6, 2x minus 1 raised to the 3/2 plus c. So this is my final answer in terms of x. So there we go. Be careful. This just requires practice. The first time I saw these, I had no idea what to do. Obviously, with years and years of practice by doing integrals and teaching integrals, this is very easy for me to do. But until you sit down, you practice, you struggle, you fail by choosing the wrong u, you try a different u, and then you succeed, that's the only way that you're going to become good enough to be able to really look at this and develop the ability to decide immediately, how should I integrate this? So don't be afraid to try and fail, try and fail, try and fail. Just keep trying over and over again. There's often different ways to approach these, so figure out one that works and then just be able to get the answer. And you can always check your answer at the end if you would like to, be able to verify that indeed, take the derivative of that, I get that expression.